about something straightforward on that. It's tree numbers. I'm not really too worried about it. Huh? It's been working since freshman year.
This slide has the full formulation for the enormity dispatch problem that ignore the transmission loss, but consider generator limits. To address the generator limit, we need to consider this problem as the nonlinear optimization problem with inequality constraints. So inequality constraints will be also addressed by adding the Lagrange multipliers, but we need to consider the KKT conditions because sometimes the multiplier need to be considered in the Lagrange function as one additional dimensions. But if but also under some other cases that such multiplier can be a 0. This slide is organized to help you to understand how to step by step to go through the formulation, the KKT conditions, and finally to find solution. So that's mathematical slides, but actually you can solve this problem using a very engineering method. So by engineering method, you just if you don't fully understand the KKT condition, so there's no worry. You only just need to still solve the enormity dispatch problem by focusing on finding the solution for each scenario, each of those 3 scenarios. So the first one is the generator is within the limit. It's not reaching either limit, or it's just reaching the one of the 2 limits. So if this generator doesn't meet any limit, the incremental cost for this generator will be same as other generator not reaching the limit. Okay, so they will operate at exactly same incremental cost as a formulation without the generator limit. If one generator reaching the upper limit, which means there's only one possibility. This generator is cheaper. That's why it can operate at upper limit, because we want to fully utilize the generation capacity of cheaper units, right? Avoid more expensive unit. If one generator is operate at a lower limit, this generator must be more expensive than the other. That's why we try to minimize its output. Okay, so that's basically what we learned from these slides. When we want to solve such a problem, if the dimension is not very high, we can just take the same approach. You start from any initial guess about the incremental cost. Like for instance, so this is the incremental cost, equal incremental cost when the total load is 800 megawatt. But when we increase the load to 975, we just need to move up this line, because all the 3 intersection points will move to the right because all the slope is positive. So when we move up this one, the intersection point will move to the right. And we just adjust, do some fine tuning about this line until the total 3 intersection points gave us the X values, which are P's. They totaled at 975. That's the idea. If there's no limit, you just feel free to go up and down until they always can give you the total load. But when the generator each has upper limit and lower limit, when you move up, there's one possibility it will reach one of the limit for some generator. If that happens, stop that machine there. Like if you move up to this level, it's the 3rd unit will reach the upper limit. Don't move further, but continue this process for the other units, because the other unit have not reached the limit. So they just optimize as a problem without limit. Okay, so eventually, so which means if you further move up, the third unit was the first unit will be there, but the other unit can further change. Okay, so this is the idea we're going to use. You can use this method to solve any homework problem, even for the problem in the final exam. So we ended at this slide. I just show you many different scenarios. Like for instance, this yellow one means the total load become 906 megawatt. Unit 1 reached the limit, but it still operate at exactly same incremental cost. But if you further increase to the target load 975, unit 1 will stop at 450, and the other 2 units will continue to increase, and so the 2 intersection points still give you the together with the 450 for unit 1 will still give you the final load. If you further increase the load, finally the unit 1, unit 2, and even unit 3, they can reach their limit, right? So the highest load this system can handle without violating the limit will be 1,025 megawatt. You can also decrease the load. For instance, if you decrease the load to 550, the more expensive one, the unit number 3, will reach the lower limit. So that is that match exactly what we conclude from previous slides. So for more expensive unit, they may operate at lower limit. We try to minimize its output. But the other 2 unit, unit 1 and 2, they still operate at incremental cost. The same one. Okay, any question? Let's move on to solve this problem numerically by Newton-Raphson approach. For Newton-Raphson approach, we can actually pick any initial guess for the incremental cost lambda. We call it the lambda 1, and we just solve the enormity dispatch by iterations. We don't need to consider the limits by this step. And in the step number 2, the step 1 give you a solution for the enormity dispatch without limits. And then we check the solution for the limits. And if we find any generator violating one of the 2 limits, we just fix the output at that limit. Because we make this adjustment, that make the total output of generation not equal to the load. So we have to continue. We cannot stop here. So if there's no generator limit to be considered, we just stop at step 1. We'll solve the problem. But because we consider limit, we have to continue. So in this step 2, we calculate the power for each unit and check the limit when we decide how much update we need to make for the equal incremental cost. Then we go back to step 1. We just iterate. Okay, let's visualize what happened. We actually pick a value, a 6, right? From the previous slides, we know this is much lower than the final answer. The final answer is around 9, at least $9. But here we start with 6. We plug in that initial guess to the first equation. This one gave you the generator output. We have 3 output. So those are you can do a quick math. So the total is much lower than the target, 975. But we can utilize the gap. The gap is really huge, right? So the target is 975. The gap is more than 800. So we plug in those gap and also the initial guess for the generator output to the second formula. The second formula will estimate how much you need to update the lambda. They tell you need to increase the lambda by more than 3. Then we move to the second step. If the generator limits are not considered, this step will solve the problem. So once you add this value to the initial lambda, so that will be the final answer. But now we're not sure because we need to check the limit. Okay, so this tell you the lambda should be updated to a 9.16. So which means we need to move up that horizontal line until this yellow line. So this is lambda 2. Then you plug in this formula to the this new lambda to the first formula again. You have 3 values for the generator output. So you compare those output to the limits. The first unit is not okay because this value is over the upper limit. So this one is not passed, but the second and third will be fine. It stay within the limit. Okay, so this means we need to change the output for unit 1 to be at exactly the limit is just valid. Okay, then we use the correct value and the calculated value here. So the gap is more than 32 megawatt. So which means we cannot stop. So that 32.89 megawatt come from the violation of the first unit. So we need to mix up this gap. So the second formula tell you need to further increase the incremental cost by 0.23. To visualize this process, which is you stop the unit 1 at fixed unit 1 at the limit, but to mix up the gap, you need to increase slightly for the unit 2 and 3 to get the new price. The new price will be $9.4 per megawatt hour. Then you check. Okay, so unit 1, you keep the same value at the upper limit. Unit 2 and 3, you get the updated value and check with the limit. So all the generators are fine. So that will be the final answer. The gap will be 0. There's no surprise. So the final answer will be those values. The same, exactly same as what we got from the previous slides by the Vero method. Any question? So this is the process you're going to take to do the homework or even do the project, the project 2 problem. Okay. If you want to use like a graphic, you put on a graphic paper to draw very accurately, so you can solve this problem. So at least you can give a very good estimate, right? Give you estimate plug into the Newton-Raphson approach. Usually it will only take maybe up to 1 iteration to give you the best answer, the most accurate answer. Yeah. So to solve this problem using this approach is not hard. If you want to in the future, if you have a chance to work with power companies to do enormous dispatch for hundreds of thousands of units, this is not going to work, right? You have to understand better about the approach we present here. Okay, so you need to rely on some computer program to do this one for you. Next, I want to talk a little bit about a specific scenario. If we decrease the output, the load to a very low value, like 550 megawatt. So this is the same problem. I just decrease the load to this value. So let's try solving this problem. Okay, so you can easily get a solution, which is this one. To visualize this solution on the graph which is like you start from maybe any initial gas. So the intersection point total will be higher than 550. So which means you need to move down. Then when you move down here, so the unit number 3, which is the most expensive unit, reaches the lower limit. But the intersection point is still higher than 550. So which means you need to further move down for the unit 1 and 2. And then you get this line, the final answer, color in magenta color. So this will be your solution. But if you take a look at this solution, So the unit number 3 operate at the the lowest limit, which is so that very expensive generator. If you take a look at the meaning for the fuel cost, that says the cost cannot be 0 because there's a constant number. The constant number really means the startup cost. So even the generator output is 0, that unit still costs this amount of money, right? Because you assume even the P is 0, the unit is still running. It just doesn't generate any IT power. It maybe only generate a slightly power to balance the local very small electricity use, but it doesn't inject any energy to the grid. Okay, so is that a good choice to let this unit run, even I don't need power from it? So maybe we can just simply let this unit be offline. If we allow to make any unit be offline, that become a different problem, not the economic dispatch. So in the economic dispatch we are talking about in this section, we assume no unit can be offline. So any unit need to operate within the limit. Okay. So even the unit is very expensive, you still need to be running at least 100 megawatt. So there's another problem which is called unit commitment. Unit commitment is include the economic dispatch as one of the sub-problem. But the entire unit commitment problem is not simply nonlinear optimization. It also have some integer variables. So this problem become mixed integer optimization problem. So which means you need to solve those variables about the generator output. Also, you need to tell whether each unit to be on and off. So if it's on, the cost function will apply. If it's off, the cost function will be 0. So you have another decision to make. If that's the case, let's resolve this problem to see if we can find even smaller cost than this best economic dispatch solution. So which means if we treat this one as a unit commitment problem, we allow unit 1 to be 0, and then the cost will be 0. Unit 2 to output to be 0, the cost to be 0, right? So we allow those to happen. So we just check each individual scenario. Since you only have 3 units, we can just check all the 3 cases. Like what if unit 1 is off? What if unit 2 or unit 3 is off? So let's first think about if unit 3 is off. Unit 3 is the most expensive unit, so it makes a lot of sense to turn off this unit. If so that's off, to solve this problem, you only just need to move a line up and down, only intersect with the first curve and second curve, not the third one. So if their total can make up the load, so that would be a solution. So here is one solution. It says the unit 3 is off, and unit 1, unit 2 together give you that 550 megawatt. So the price is this one is higher than the incremental price for the first one but you save the cost for the unit 3. So the final total cost of the system is smaller than the original solution. So by turning off the unit 3, you can save some money. There could be other cases, like what if the unit 1 is off? If unit 1 is off, you move this horizontal line only intersect with the second and third curve. So the cost is higher, right? Not smaller. So this is higher than the opposite way. So the solution B is cheaper than the solution A. And solution C is more expensive than A. Okay. The third one will be turning off the unit 2. So you move a line intersect with the curve 1 and 3. And this one is even cheaper than A. Okay. So finally, the solution D will be the best solution. Yeah. Okay. All right. Any question? Is it clear? Okay. So let's move on. So the only thing left will be about how to deal with transmission loss. So in the formulation we studied so far, we ignored the transmission network. When the transmission distances between generation and load are very short and load density is very high, so we can ignore the transmission loss. And finally, the conclusion is all power plant will operate at the same equal incremental cost for the optimal dispatch. However, when we deal with a large interconnected power network, so we may have to consider the network topology because power delivered over long distances through, if there could be the low load density areas, the load is very distributed in the system. So we have to calculate the transmission loss of major branch or each branch or at least some of the major branch. Otherwise, the loss will affect the dispatch result. So we need to figure out what the transmission loss is, and then we add this loss to the formulation and to study how to solve that problem. So if we want to know the accurate transmission loss, the only way is to solve power flow, which is same as what we did in the section 6. So in the power flow problem, when you solve power flow, you calculate transmission loss of each line and you add all the losses together. So that will give you total loss. Then you add that loss to your formulation to do the economic dispatch. Which means you have to go through this power flow problem and then you count the total loss. In this section, we only focus on the approximate calculation of a total transmission loss. The total transmission loss can be assumed as a function of all the generator outputs. It can be a linear function or a quadratic function, or even you add higher order term. But usually quadratic function is good enough. For instance, we can assume the transmission loss to be a function of the summation of many items. So B0, just model some constant transmission loss. As long as your system is operating, there are always this loss, which means the loss is always higher than this value. There could be a part of a loss which is linearly depending on the generators. And also there's a second order term depending on the product of the output of two generators. We want to find out this formulation, and then we can consider it in the problem. So let's find the transmission loss as function of all generator outputs. If we use this simple system as one example, we have two generators connected through two transmission line together to power a load. That's just a single load. Okay. So the system has only 3 branches. Okay. To calculate the transmission loss for the entire system, we need to calculate the loss for each individual branch. The branch 1, 2, and 3. Right? We need to know the loss here, loss here, and the loss there. So we then add those together. And each transmission loss is a function of the current. So if we know the resistance, it will be a quadratic function of the current magnitude. So tricky part will be calculating the total current at going to the load. using the Kirchhoff current law. So that current will be current 1 plus current 2. Which will form a triangle because all the 3 current vectors are phasors. Because we only want to know the magnitude of current. So the magnitude of I3, which is the length of this line, this phasor, will be the longest edge of this triangle. So if we draw this line, which is like the height of this triangle, so the absolute I3 will be equal to this part and plus that part. So which will be absolute I1 multiplied by the cosine alpha and absolute I2 multiplied by cosine beta. All right, so now we're ready to find the quadratic function about the loss, about all the generator output. So the loss for this system only have 3 components, right? 3 branches. First branch, basically I1 will be just, so we know this formula, right? P is equal to I V then cosine power factor. So I will be, absolute Y will be P divided by V and the cosine phi. So this is what we learned already from section 2. So which means we can replace absolute current by using the expression using the active power factor, and voltage. So this will be I1, I2, and I3 here. We just borrow this one. So it will be a sum of 2 expressions. So each depend on one of the generator output. So next, you just move the P1, P2, right, outside. So it has to be a quadratic function. It has to be in this form. So if the system doesn't change the topology, doesn't change the parameter, and our even operating condition will be about the same, you can always do such solving power flow. And finally, when you calculate total loss, it will always be similar to this quadratic function. So you just need to find out the parameters or coefficients for B, B11, B22, and B12. B11 indicate the cost only depending on the branch connecting the first generator, right? B22 is the branch connecting the second generator, and B12 rely on the branch from the load to both generator. So it just where the energy can merge from the power plant to the load. So which means if you have even it's a very complex network, you have many generators distributed, which together power a load center area. So for this case, the transmission loss function will be very simple. So the cross independence between the generator output can be ignored, if this is the case. Okay, but if you do have a network, so when you add those coupling lines, so the third term cannot be ignored. All right, so we can introduce a more general formula for this answer, so which is called the Korn's loss formula for network with n generators. So we just assume the transmission loss will be this quadratic function. So which is a generalization for the network of any generators. Those B coefficients can change with the power flow, but usually can be assumed to be constant or estimated based on some base condition. So if your system don't change significantly from that base condition, so this formula can still be used. There will be more details in the chapter 7.7 if you're interested. Okay, so let's see how we solve this problem. So everything in this pink or magenta color will be about transmission loss. So if you ignore any such thing, that will be go back to the formulation for enormous dispatch with generator limit, but without losses. Okay, so we just add this transmission loss. So quickly go over what we conclude so far. So for each cost, for the cost of each generator, if we calculate the derivative with respect to the output of that unit, so that gives us the incremental cost, right? This is because the cost we have considered as a nonlinear function in quadratic form. So which make the incremental cost for each unit to be linear function. So this is the straight line in our graph. We have many straight lines of different slope of different ends. So we just move a horizontal line to intersect with all the lines. This is one of the such lines. If there's no limit, and when we move up the horizontal line, it always intersect with all the lines, and the intersection point will tell you the final solution. If there's a limit, some line may stop at the one of the limit, one end of the line. So, but the other line can still move. So what we add to this formulation is the transmission loss. Transmission loss is a quadratic function. Then we can calculate a partial derivative of the transmission loss with respect to each generator output. So this has to be a linear function. It's a derivative of the quadratic function, so this one will be linear. So we call this item as incremental transmission loss, similar to the incremental fuel cost compared to the first equation. Incremental transmission loss means if we increase the output of this unit, how much loss will be added to the network. So it's a linearly change. Okay. Next, we update the Lagrangian function. We still have the total fuel cost, and we have the penalty about violating each generator limits. And for this penalty, based on lambda, that's actually the penalty of violating the power balance equation. Because now the power balance equation become this one. So we have to add the transmission loss. The total generator output need to be slightly higher than the load to compensate the transmission loss, PL. So we need to add that PL into this formulation. So lambda here is not the penalty for violating the power balance, right? It's the penalty violating the balance between the total output and the load and also the transmission loss. But still the penalty of violating the balance of energy or power for the entire network. All right, so next step, we expect the gradient vector of the Lagrangian to be 0 if no limit is violated. So this is still true. We still can take this approach. So the first type of element is Lagrangian, the partial derivative of the Lagrangian with respect to the lambda, and the second is with respect to each power output. So there's also other element about the mu and the gamma, so we can address later, similar to what we did for the formulation with limit. So let's see what those two elements are. For partial L by partial lambda be 0 is equal to 0 means basically just means that this equation, this equality constraints. Second type element, partial L by partial PI is equal to 0 is now become this one. Okay. If you compare to the original incremental cost. So there's a one item added here, which is about the transmission loss. So we slightly rearrange the second equation. So that tell the incremental cost of each unit plus lambda times the incremental transmission loss of with respect to each unit will be lambda. And we further simplify this one. It tells the incremental fuel cost of each unit is equal of so the lambda, the multiplier lambda is equal to the incremental fuel cost of each unit multiplied by a factor. That is lambda. So lambda right now is not exactly the incremental fuel cost for each unit. We need to consider the factor due to the transmission loss when this generator is sending power to the load, because different generators have different distances to deliver energy. So that makes a transmission loss be different. So we can treat this entire thing as the incremental cost seen by this unit at this position. But if we look at that cost from different points of network, such costs are different. Why are they different? Because they need to consider how the transmission loss can influence that cost. So when the transmission loss is zero, that if we assume this is zero, so transmission loss doesn't change with the power output, this entire factor become 1. So that go back to the original case when we ignore transmission loss. Okay, does that make sense? So if you, in this slide, you get rid of any items colored in magenta, that's exactly same as the approach or formulation of the original one without transmission loss. So finally, transmission loss only change here. So if you understand what this one means, you have better, you know why we do this one and how we solve the problem. So if this is 1, lambda is equal to this one. This one is, by definition, it's just incremental fuel cost for each unit because DCI by DPI, right? Only about 1 unit. It doesn't depend on network. And if this one is equal to lambda, which means all units have to operate at the same incremental cost, which is lambda. So that means all generator will operate at the same price. But because we consider transmission loss, so when you sell electricity, you're not just selling electricity to your terminal at the same location. It's just like you package electricity to ask a truck to give electricity to the user. You have to go through the power network. Then the transmission loss need to do a little bit fine tuning about your incremental cost. So if you deliver electricity through longer distance, the transmission loss will be higher, which means you need to make this one be slightly higher, need to pay additional price for the transmission loss. So that make eventually all the unit operate not exactly at the same incremental cost, slightly different. The difference is really depend on the transmission loss. So this is what they changed. Okay, so finally, we need to solve this equation. Okay, so if you think about get rid of any like a colored item, that go back to the original same simple equation, right? So go back to our very beginning slides. We only need to solve this linear equation. So that one can be analytically solved. You just take step 1, step 2, and you get the answer. But right now, by considering transmission loss, you add those pink items. But the approach is still the same. If you're able to solve this equation, that tell you the lambda, that also tell you the PI. So you just need to list such equation for all generators, like from P1 to Pn together plus lambda. You have n plus 1 variables to calculate. If you have any approach, you can solve such equation. That will be the final answer. But definitely, you also need to check the limit of generator. Okay, so you have to rely on the Newton-Raphson approach. This is not required in the project by homework, but in the project, I gave you assignment so you can check how this transmission loss may affect the final answer. so the same approach can still apply by using Newton-Raphson approach. The first step is to solve economic dispatch with no limit. But here, the economic dispatch means you need to solve all such equation for economic dispatch. And during the iteration, if any generator reaches the limit, you just fix the value at the limit. Then it returns the step 1. So just iterate until you find the answer. Okay. Any question? Pretty simple. Actually, logically speaking, it's pretty simple, right? But you just need to work on the homework. But yeah, this is not required by homework. I just want to give you some idea on how the transmission laws may affect the formulation and also the approach. Just give you one example. This example is not required. It's in the textbook. I just present this example to give you some feeling about how the laws might change the final result. So if we dispatch 3 units, each has a cost function C1 to C3, and also we have generator limit, and we add a very simple transmission loss function. So it's a quadratic function, but we ignore any like a Bij. So for the cross term, we just treat. So this is similar to be maybe a 3 generator together send some electricity to a center location. So transmission loss only depend on each generator output individually. Okay, not their total power. So that formula is actually in per unit. We can translate that formula into the unit of megawatt by multiplying the 100 MV base value. So this formula will be in the unit of megawatt, so which is more straightforward. If you solve this problem, okay, the final answer says, so this is P1, P2, P3, and this is lambda, and the total transmission loss only take about 1.7 megawatt compared to the total load. The total load is 150. Okay, so only that take about 1% of the system load. This is not much. So which means we can solve this problem. Let's solve this problem by ignoring the transmission loss. So if we ignore the transmission loss, we just get rid of cross off this equation from formulation. You just solve it as no transmission loss, and those are the answer. So if you compare the answer to the true solution, lambda changed by about 2%, and this change P1 changed the most, but because P1 is smallest one, so the true answer is 35. But if you ignore the loss, the unit 1 is generating about 32, and the others all at a similar value. The final total cost is only different by less than 1%. So it's not too bad, right? Okay. Yeah, so that's the last thing I want to talk about. So the quick conclusion is, if you do the economic dispatch, even you ignore transmission loss, that doesn't change your answer significantly. It can maybe create about 1 to 2% of the difference in the final answer. If you really care about 1 to 2%, then you need to consider transmission loss. But 1 to 2% for a large power system can be huge, can be a lot of money. There's one additional slide. So this is not required, but I try to organize that section in the textbook about how to solve the economic dispatch using Newton-Raphson approach, considering both generator limit and transmission loss, because our target is to solve all such equation we put together. How do we solve this equation? So I just draw this flow chart. So all such equation will be n such equation for all n generators, add additional one equation for power balance. So how do we solve those equations? So actually, those equations together are not more complex compared to power flow equation. So if you write down power flow equation compared to this set of equations, so power flow may be more tricky because there's a sine, cosine function, or even you consider real and imaginary part for complex power. So for this set of equation, we want to use Newton-Raphson approach. We want to make sure the limits to be satisfied, which means during the iteration, if anyone reaching the limit, you need to stop there. Don't further change that value. Using Newton-Raphson approach, so this will be process. It's pretty standard Newton-Raphson measure. You just start from an initial guess and iterate. Okay. So that's the last thing I want to say. And on Friday, we'll talk about the course project with some background material. Okay.